Hello and welcome to Optical Pumping. I'm Kyle Funk. Experiment and data collection was made with my partner Shauna Bailey. So we're going to be looking to use a rubidium radio frequency discharge lamp combined with lenses that will circularly polarize our light, as well as a heated rubidium cell to achieve our optical pumping. The cell contains two isotopes, rubidium 87, rubidium 85, and it can be adjusted from temperatures of 37 to 97 degrees Celsius. Boltzmann coils are also added in the vertical and horizontal axes to produce an external magnetic field. We're going to be looking to calculate the maximum absorption cross-section relations to the Zeeman effect to calculate Earth's magnetic field, G-factor ratio between our isotopes, the resonant frequency-induced peaks, as well as observation of transient effects due to excitation and de-excitation of electrons in quantum states. Our resultant data gave us a cross-section of about 0.910 plus or minus 0.053, which was nearly a factor of 10 less than the accepted value of 10 times 10 to the negative 16. And Earth magnetic field of 71.1 plus or minus 1.1 microtesla, which is about 20 less than the accepted value. G-factor ratio of 1.74 plus or minus 0.12, which is about 0.25, and clear observable transient effects, along with a relatively increasing decay frequency as amplitude voltage was increased. So for our experimental methods, we're going to be using a component structure as shown in this picture here. While varying our oven temperature and keeping an input voltage constant, we can find this cross-section fitting it to I equals I naught e to the power of rho L sigma, where this is our input voltage, I naught is our input voltage, rho is our atomic density in atoms per meter squared, L is our path length, and sigma is our cross-section that we're trying to find. Taking these steps in 10 degrees Celsius from 37 to 97 degrees Celsius, we fit it to ODR package in Python. To the form y equals ae to the power of b times 0.025 times x, where a is a free parameter as initial voltage and b is our calculated value of sigma. To find the Earth's magnetic field, we're going to use these Boltzmann constants, or these Boltzmann coils, as in a sweeping manner, so that at a time we'll see a 0-point peak, as well as organizing polarizing lenses set at angles of 45 degrees. To create right circularly polarized light that allows for excitation of our electrons. Finding this value of this 0 point, we can find the vertical and horizontal components of this magnetic field, and this will be our negation of the Earth's magnetic field and thus the magnitude of the Earth's field here. Following a similar component structure before, we've added a function generator, a radio frequency function generator, to calculate our G-factor ratio. So when we add our radio frequency function generator, we're able to see resonance peaks as we change our frequency from 50 kilohertz to 150 kilohertz. And we can measure the time spacing between the 0-point field and these resonance peaks as we increase them. And the ratio of these two slopes will be that G-factor ratio. To observe our transient effects, another function generator is added to this component structure here, where our starting magnetic field amplitude is adjusted so that the larger satellite peak matches a falling edge of our sweeping magnetic field. The second function generator is used to generate a square pulse of 5 Hz that is turned on and off. With appropriate gain settings, data is collected and fit to another Python ODR. And this equation is y equals d times e to the a x times sine b of x plus c plus v, or plus f, where d is our initial amplitude, a is our decay constant, b is our frequency, c is our phase difference, and f is just a free parameter. So for our cross-section, we found using this graph here that it was 0.910 plus or minus 0.053. When the reduced chi-squared was about 10.839, indicating an overfit or an underfit to our data, so too much error associated there. Our 0 point using these conversion factors and this sweeping fields in the vertical and horizontal. We see the 0 point field here and the sweeping here. This magnitude and error propagation, or using error propagation to find this magnitude, we found it to be about 71.0 plus or minus 1.1 microtesla. So for calculating our G-factor ratio, we have an example here. This is our 0 point and our resonance frequency induced peaks. As we increase frequency, we can measure the time spacing between these peaks, and that's what we have here for our graph. Fitting the slope of the upper line over the bottom gives us our G-factor ratio, shown here, which is 1.174 plus or minus 0.12. Kind of error tied to the 1 kilohertz error associated with our frequencies and the 0.004 seconds for each time point in our oscilloscope. So looking at our transient effects, we have an example here as well as a fitted for 3 volts. Our table here shows our increasing amplitude, decay constants, decay errors, frequency errors, as well as our reduced chi-squareds, which show an underfit to our data, which means we had too much error. This error is probably the 1% that we've tied to our oscilloscope measurements. So looking at some of our calculated values compared to accepted values, we see our optical absorption cross-section about a factor of 10 less than our accepted. So a lot of this error associated is from the conversion from temperature to atomic density from the table that we were given. It's a rapid variation of the density, which is subject to much error also. So looking at Earth's magnetic field, it's pretty close to theory, but error is mostly tied to given conversion factors because this equipment has some wear and resistance, and then some photodiode and scope errors. Our G-factor ratio is pretty close. Most of this error is just tied to time cursor measurements in our oscilloscope and photodiode precision. And for our decaying oscillations, we're seeing a large chi-squared indicating an overfit to all of our datas. And this error is mostly tied to the stimulation of the optical table while conducting measurements and the influence of other external fields in the room. So taking a look at these results, our calculated cross-section was about negative 90% off from the actual value. Our Earth's magnetic field was about 37% off. Our G-factor ratio was a lot closer, only giving us about 16% error. And our transient effect decay constant range was from about negative 895 to negative 546, but kind of not in any particular order. Frequencies do tend to increase as the amplitude increases, but we did see a decrease from 3 to 4 volts. Reduced chi-squareds in this case are also range from about 8 to 28, so this is an overfit to our data. So looking at all of our values in total, we yielded pretty relatively inaccurate for our cross-section, pretty close for our Earth's magnetic field, very close for our G-factor, and pretty observable increase in frequency other than this, as I said before, 4 volts here, and decay constants kind of range, go up and down. So this lab did help us in familiarizing error propagation through measurement and narrowing error sources down, as well as operation of lab equipment and calculations using Python's ODR to fit data to formulas.